I'd like to welcome Professor Michael Shaver. He's going to be presenting his inaugural lecture to us today. Mike joined the Department of Materials in 2019 and is a Professor of Polymer Science, where he leads initiatives in sustainable polymers, plastics and materials for the school and the Materials Department. He is also the Sustainable Materials Champion for the Henry Royce Institute, which is the UK's National Advanced Materials Science Centre. Following a PhD in his native Canada from the University of British Columbia and an NSERC postdoc fellowship at Imperial College in London, he began his independent research career at the University of Prince Edward Island before moving to Scotland in 2012, where he was a Chancellor's Fellow, Reader and finally Professor of Polymer Chemistry. He leads the Green Materials Laboratory on the development of sustainable materials, including new motifs for renewable, degradable and chemically recyclable materials. His work ranges from fundamental projects rooted in monomer design to working with industrial partners in plastic packaging, medical diagnostics and sustainable materials. He was the inaugural editor-in-chief of the international journal Green Materials before his current role as editor of the European Polymer Journal and has published well over 100 papers. He's also been recognised with over 80 invited plenary lectures, the Macro Group Young Polymer Scientist Award in 2015, Young Academy of Scotland 2014-18, amongst many other awards. At this point, I'd like to welcome Mike to the virtual podium and begin his lecture with us today. So thank you very much. Handing over to Mike Shaver, who hopefully can share his screen with us.
I hope I can share it too. Let's see if this works. So hopefully you guys can all see something. Quite dramatic, perhaps. So oftentimes when I give a lecture to the public, I like to start with this slide. And it's weird to begin with the end, but oftentimes when we think about the state of the world, it sort of feels like this. And this is particularly true in you know, our current circumstances. We've got coronavirus transforming a in-person inaugural lecture into a virtual event, which by the way has its benefits. I think there's people from all over the world who have been able to tune in that wouldn't be able to be present otherwise, so that's a good thing. But we've also got, you know, some major challenges from the environmental front as well. And so oftentimes I'm pitching around plastics and how me being a polymer chemist, we're destroyers of the earth, right? It's all going to end pretty soon because of the environmental crises that we face. So I like to sort of start with that, but then kind of bring that in and talk a bit about where I'm from and where we're going. So inaugural lectures are a cool thing that is very UK focused, I think. So for those of you who are from universities abroad, this might be an unfamiliar mechanism, but I think it's pretty neat because it kind of allows you to do something a bit unusual, which is talk about the journey that you've been on. And so to start things off, I'm actually gonna like just jump back to that end of the world bit and really talk about something which is perhaps a bit unusual for an inaugural lecture. And that's to talk about where I came from in terms of growing up. So when we think about all those crises that are going on right now, one of the ones that I think is particularly prescient and should be on our minds is Black Lives Matter and those protests that are going on. So I picked a photo of my family. So this is my brother and my sister from when we were very young. I think one thing that lockdown has done is I've been able to reproduce the exact same haircut that I had so many years ago, which is good. But you know, growing up in a mixed race family, having the opportunity to go to an African Baptist church has really, you know, shaped my view on race. I think it's really important for people who aren't Black to talk about this in a very open way, to really speak openly about diversity and where it needs to be challenged and how it needs to be supported. So I just wanted to start by sort of setting that up as an important thing that certainly I welcome conversations about both here and abroad. So I guess I sort of in a transition there wanted to start the lecture with a bit of a journey, a sense of where I've come from and how I ended up here. So been all over the world. You can tell I haven't really picked up an accent from wherever I've been, but I'll take you through a little path. So Google Maps is helpful for representing this. And really my academic journey started, in this transition from my home in Nova Scotia in Canada, and a pretty short drive considering to Mount Allison University. Mount Allison University it's an odd little university. So the town celebrated when it got its second stoplight. It's an extremely small place. The village really that it was in would double in size when the student population arrived. And so we had extremely small classes, extremely good mentorship. And really my whole career started because of one person, and that's Steve Westcott. He is notorious for not wanting his photo taken. So this is one of like 5 photos in existence of Steve. But because this is such a small university, you had a really neat pathway, because each month in the summer, all of us undergrads would, work in the lab. So we would start doing active research very intensely from a very early stage. So I had 5 published papers from my undergrad, worked on catalytic hydroamination and hydroboration. So very much a hardcore inorganic chemistry topic. And then my final honors thesis, I worked on new platinum compounds as anti-cancer agents. So absolutely thanks to the very unique mentorship of Steve, who would tell it like it is at all points of the day. Absolutely convinced I'm an inorganic chemist for life, because that's what he was, and I very much wanted to be like him when I grew up. To talk a bit more about Mount Allison, being such a small university, we had really tight-knit graduating classes. So my graduating classes from chemistry was 13 people, so 13 people only. And to go from that to a very large university like Manchester is pretty dramatic. But in that graduating class of 13, there's 3 professors and 2 other people who are involved in academia. So myself in Manchester, Paul Hayes in Lethbridge, and Steve Fletcher at the University of Oxford all graduated in the same graduating class. And then Paul and Karen are also involved in academia in various roles in Canada and the US. And so to take a graduating class of 13 and say, okay, we've got 5 different academics is really remarkable. So it was a unique place that was very formative for me, really transformed the way I think and work. From there, I knew I wanted to do a PhD, and thought a lot about where I would want to go. And I think at this stage, I was ready to perhaps make a little break for my parents. So Nova Scotia is here, right? And you can see the distance between my home. So this was a 2-hour drive, right? And I was like, well, I wanted to stay in Canada, but I wanted to go as far away as I could while still being in Canada, right? So my parents weren't able to show up easily. It was now going to be a big journey for them. And while we didn't drive, it's useful to think about Canada and how large it is by this pictorial and how far you could get across. This really was a move to stay as being an inorganic chemist. And I wanted to join one of the best inorganic groups in Canada at that time. And this was joining the group of Mike Friesick. And his focus was really on trying to exploit metal-based complexes to do very difficult bond transformations. And so my focus was on group 5 metals, so vanadium, niobium, and tantalum, and doing a lot of different small molecule activations from nitrogen to phosphines to alkynes, and still really felt like an inorganic chemist. UBC is a absolutely fantastic, stunning campus. I think it's the only campus in the world that has a golf course and a nude beach. Fantastic place to visit, and Vancouver is one of the best cities in the world, really. So definitely appreciate my time there. And I think what's really neat about this is that you definitely had the opportunity to be independent and gain skills and try and learn a bunch of new things. For me, this is a lot of skill-based development. So learning how to do air-sensitive synthesis using slink lines, learning how to solve my own X-ray crystal structures, doing my own DFT calculations, so dabbling in theory, and developing my own NMR techniques. So really being able to have hands-on access to the world's best equipment, this was the first time I really was able to do that. won a lot of awards. Canada is actually remarkably good at supporting young talent. So they're able to give you scholarships that allow you to go wherever you want in the world and be trained by the best. And this is also the start of mentorship. So this was my first time where I really realized how much I valued mentoring other people. I've always felt value in being mentored by others, but this was the first time that I really got to mentor others. And this has really shaped my career because I've always sought out opportunities to mentor young people. Well, not even really young. I guess that sounds a little ageist. Mentor people who want to be mentored and are seeking some sort of a different perspective on the things that they do. The other big thing that happened when I was in Vancouver was I got to meet my wife. So she was also at UBC at the time, got her master's there, and I can confirm she's as excited to be married to me today as she was in this photo. Really, it's remarkable the journey that we've been on together, and I think we are very much a perfect pair. She is exceptionally supportive. And whenever I've said, okay, let's go and do something different, she's been absolutely behind me 100%. She's exceptionally talented in her own right, working at AstraZeneca now, but has worked in a variety of different science roles throughout her career, and is very much a, I guess the sun around which my planet rotates. So I'm very appreciative of her. So from there, I was awarded this NSERC postdoctoral fellowship, and that allows you to do a postdoc wherever you want in the world. I was awarded this and had a conversation with Lisa. We were dating at the time, and we were like, well, we don't want to go to the US. That was the only caveat. She was like, wherever else is fine. Thought that London would be cool. Coming to the UK would be neat. And I knew I also wanted to try something a little bit more applied, right? So I wanted to be a little bit more towards an application of inorganic chemistry. And so this is the first real transition that we made as a family unit. I actually proposed in a bit of an awkward way where I was sort of like, oh, are you going to need a visa to go to London with me? Do you want to just get married? And then we went ring shopping together. So let's just say we're not the most romantic couple in the world. But this transition, this flight across was really transformative as well, because it was a really big group led by Vernon Gibson at Imperial College. And this was my first time actually doing polymer chemistry at all. So now I'm a professor of polymer science, but this was my first foray into this application area. And this is applying my knowledge of inorganic chemistry to catalyst design, kinetics, mechanism. We were working on atom transfer radical polymerization and really inventing organometallic mediated radical polymerization as a term. It was a big group with a lot of industrial funding. And so this is very different to go from something which is very fundamental to something which is very applied. There was a lot of devolved leadership, so I had to take responsibility for a team and mentor them up. And it was through that role that I met Laura Allen, who was the first mentee, I guess, who was really important to me and important to my career. So Laura is has followed me through a number of different steps, and she'll crop up a few different times. The next thing that happened in terms of Imperial is I realized that, beer wasn't boring. And so we picked up a camera good beer guide, decided to wander around all the different London neighborhoods. And in fact, we hit every single pub in the 2007 good beer guide that are within the London postcodes. And that's actually a remarkable number of pubs. And to get two Canadians just showing up on some N17 pub doorstep was a pretty neat experience. We got to meet a lot of people and saw a side of London that I think even many people in the UK haven't seen. Still certainly think of myself as an inorganic chemist at this stage. I started to build this network up. This is a photo of Laura kissing Steve Westcott. So this is the connection of my different past selves, which kind of has continued to this day. So the next step was really the idea of starting an independent career. And to be honest, at that stage, I never even considered staying in the UK to work. And I don't know why that was. I think perhaps we were a little bit tired of London at that point in time. But I had this idea of wanting to go back to Canada. And so we went back actually quite close to home to the University of Prince Edward Island. Most people who hear about the University of Prince Edward Island have never heard of it before I introduced it to them. But again, a very small university. You can liken it to if they had built a university on the Isle of Wight. That's my best UK comparison. So very different perspective, because most of those students would have come from the island, had grown up, many haven't traveled very far. And so they've got a very different perspective on life. Because it's a very small place, we really had a very few number of faculty there. And indeed, I was the only inorganic chemist, even though I was already sort of stretching into polymer chemistry at that time. It's very predominantly undergraduate. So it had 2-year MSc degrees. And actually, when I was there, I got frustrated at not having a PhD program, so I just created my own. And this was, in fact, the first PhD program at the entire university in the core sciences. Laura returned to my group, so she came over and worked as a postdoc for several years. And Mitch Perry, who's another person who was really important, came and finished his MSc with me. So he was an islander who then is going to again feature later on. And listen, Prince Edward Island is a fantastic place to raise your kids, to go to the beautiful beaches, to visit Anne of Green Gables. If you've read those books, that's based there. Many people think this was a real character, but this is our equivalent to visiting Disneyland. And really, it was a neat place. But being such a small place, when we had first had some research success, it was clear that there were a lot of limitations in terms of us being able to do what we were going to do. And it became clear that we were going to move on at some point in time. The other thing I do need to mention kind of at this stage is on top of my wife and on top of science and on top of craft beer, the other thing that's really important to me is our dogs. So this is our first dog, Freddie in the middle, the black one, and in the back is Sam, the corgi. Freddie passed away, unfortunately, several years ago, but Sam is still with us. Although he has switched seats, so you can no longer see him in frame. And I'll talk about the third dog, who you can see in a bit. So the next move was, again, you can see how much my carbon footprint is increasing just from flying around to different jobs, was a move to the University of Edinburgh. And this is as a Chancellor's Fellow and a reader at the time. So was always called professor, right? Because in North America, you're an assistant professor and an associate professor, and everybody just calls you prof. Suddenly I'm demoted, no longer prof anymore, and I'm supposed to read things, I guess. So getting used to that different system in a different country is a challenge, but I think I'm almost there now. Interestingly, because we had been doing so much polymer science, I actually got asked what section I wanted to join. So they were like, well, we're going to hire you and you can join physical chemistry or organic chemistry or inorganic chemistry. Still felt like I was an inorganic chemist in terms of the teaching sense, at least. So chose inorganic and still very much inorganic chemistry. But it was a tough call. I really did think about it at that time. And really at that point in time, I was thinking of myself as a polymer chemist, right? So this was the first real mental transition for me. When I was there, I arrived and I had negotiated everything else, didn't actually negotiate an office. And they had this archaic rule that if you had the word fellow in your name, even if you were a reader, you got to share an office. And so I got to share an office with Steve Thomas, who's the top photo here. Steve had just joined also on a Chancellor's Fellowship, but at the lecturer level. And really this was so important to me because I needed to learn the ropes. I needed to understand the UK system. I needed someone to go down to faculty coffee with me so I didn't feel like I was alone, and really helped shape my time there. Steve and I collaborated on a lot of different stuff. So he's a synthetic inorganic chemist, does a lot of work on catalysis, and helped translate a lot of the stuff we were doing on polymer chemistry into small molecule chemistry. Two other key people from that time that really need to be mentioned are Neil McEwen, who's another polymer chemist. I shared a lab with him when I was in Edinburgh, and really helped me calm down a bit, I would say. So whenever I was getting stressed about something, he would be like, it doesn't really matter, and really give me perspective on life and what's important. And the third, and certainly the one that's continued most of this day, is Jenny Garden. So Jenny is also a polymer chemist, came from Charlotte Williams Group, but joined as a fellow, and I was assigned to be her mentor. And by far, she is the best person I've ever mentored, both in terms of a personality perspective and in terms of just a willingness to soak it up. She is really, really, really keen to get mentored and to apply that mentorship. I think she's an exceptional young talent. Tried to recruit her to Manchester, and she wants to stay in Edinburgh, so failed at that. But I think she has exceptional promise in being a key player in sustainable polymers for years to come. And just to show you, so Sam came over from Canada with us, and then we've also had Callie. Callie's a rescue greyhound, and she is a delicate flower, whereas Sam is tough as nails. Callie gets injured by walking down the street. It's remarkable how many times she hurts herself, but she is a wonderful, sweet girl and a beautiful little princess, and looks good in a pink bandage, I think. But at that time, so I kind of got this promotion. You know, you get to choose your title, so I'm professor of polymer chemistry. But I was sort of wondering what the next step was. We were really trying to solve some of the big challenges in synthetic polymer chemistry, but realizing that those challenges were more systemic than synthetic. And so I would say I was having probably a bit of an identity crisis, wondering whether or not I fit in a traditional chemistry environment. Am I really a chemist? I remember a coffee with a colleague where he said, because I work on macromolecules, it means I don't know what a molecule is, and therefore I'm not a chemist. And really was looking for a change that would allow us to as a group, address some of the really big problems in polymer chemistry. And so what do you do when you have an identity crisis? Well, you move to Japan for 2 months to reflect. So I was a visiting professor at Nagoya University for 2 months. And it was in those 2 months that I actually sent in the application package for the post I'm in now. Get shortlisted for interview, meet Bill Sampson, go for a walk in the wilderness with Phil Withers, and they try and cajole me to come. But really the big reason, I would say that the nail in the coffin, so to speak, was a super odd trip to Reasons to be Cheerful. Now, Reasons to be Cheerful, if you're Manchester based, once the pub's open, you need to make a trek down. So this is just outside of Burnage train station. Lisa had gone there on a kind of scouting trip to see whether or not there were housing districts we wanted to live in. But we walked into Reasons together for the first time, sat down at the bar and met, just started talking to the bartender, met the bartender, Abby. And I was like, oh yeah, that seems like a cool place. And she's like, oh, well, it's my last shift. And I was like, oh, what's going to go on? Why are you leaving? She was like, oh, well, I'm starting a new lectureship position. And I was like, oh, you're an academic. She was like, yeah, I've just signed in this contract now. I'm going to start this new lectureship position. And I was like, well, what school are you in? Oh, I'm going to be in the School of Law, right? So I was like, that's pretty cool. Well, I'm here, right? I've just been interviewed for this position. I'm going to start signing contracts and agreeing to come down. And that's really neat that we've met in this very odd circumstance. And so the guy who's sitting next to us, unrelated, just had been coming in and sitting down, pipes up and asks what I do. And I say, well, I'm a chemist, but I'm going to be joining the School of Materials. And he says, oh, that's neat. I did my PhD in chemistry at the University of Manchester. And I was like, well, that's a pretty odd coincidence. And so we get talking to him and he's like, oh yeah, now I work at AstraZeneca. And he's, we ask him what he does. And he says, oh, my role is analyst in chemical methods. What is it? Chemical development, right? And it's the exact same job that Lisa has just secured an interview for at AstraZeneca. And when she goes to AstraZeneca to interview for that position, which she eventually got, the tour was given by this guy we happened to randomly meet in the pub. So we go to a pub by chance. We meet a bartender by chance who's starting a new academic position. The guy sitting next to us has the exact same job that my wife now has. So again, I'm not someone who believes in signs, but I do now, because that was pretty freaky. We then decided to rent nearby and then buy a house nearby. And I really, truly value the community that is Reasons to be Cheerful, which has very much shaped and driven our lives outside of work since we moved down to Manchester. So take home message one, because I'm at kind of the end of my journey now. I think one thing that's true about me is that academia has never been about consistency. I don't feel like I'm constrained to do the same research or think the same thoughts or live in the same place. The ability to change topics, what I teach, what I research, what I innovate in, and align that to my interests and ambitions has been so important to my career. So I'm immensely privileged, I realize this, to be afforded so many different opportunities in so many different places. And I think the ability to grow from those opportunities, driven by the support that I get from Lisa and my family, has been super important. So part two, well, I talked about why I'm making these decisions. Probably talking about the why is going to be important. And really, this comes down to us having a crisis on our hands, because we've got a lot of plastics in our environment and we don't really know what to do with it. So we all have choices to make, right? And we're all contributors to the fate of our universe. And so oftentimes I'm giving a public lecture. This works much better in person. I ask people what kind of glass they would want to use. What would they want to drink their beverage out of to save the world? So do you want to use a styrofoam cup? Do you want to use a glass vessel? Do you want to use a ceramic mug? And I get people to raise their hands, you know, who's going to choose the styrofoam cup? Who's going to choose the ceramic mug? And when we think about that, and we think about that in terms of energy instead of materials, we realize that we can make, transport, use, and dispose of 500 styrofoam cups for the total cost of one ceramic mug. And so if we want to use the mug, we've got to consider the fact that we've got to dig up the clay, we've got to fire up a kiln to high temperatures, we've got to transport that heavy mug to, you look like a Waitrose crowd, Waitrose, you've got to pick that up from Waitrose, you've got to bring that home. All of that energetic cost has to be taken into account versus something which is extremely efficient to make, efficient to use, efficient to transport because it is so lightweight. And so there's an energetic difference there in terms of how we would use it. Now, some of you are going to say, okay, we can reuse our ceramic mugs, right? And if I use that 501 times, well, that's going to be better, right? In terms of the maths, I'm going to be able to save some energy because I used the mug in that way. Now, the thing is this, is I would ask you whether or not you want to wash that cup. Because if you want to wash that in hot water and detergent, you have to heat the water up and you have to clean the water. And that's the energetic cost of 2 styrofoam cups. So we have a real challenge here in understanding the relationship between our material world and energy. And it's that decision about what is best from an energetic perspective that's going to drive our decision-making moving forward. And so if I then think about the broader realm of plastics that we interact with, and we think about what would happen if we tried to replace plastics with any existing material that we have, well, we would quadruple plastic packaging waste. We would double food spoilage because of how exceptional plastics are as oxygen and moisture barriers. We would have much heavier vehicles because we would have to replace those plastic parts with other alternatives, increasing our petrol costs. And we would have to replace our modern insulation, which is predominantly plastic-based, and dramatically increase our energy costs. And so this has been estimated to be a ridiculous number, 583 million gigajoules of energy per year, which none of us understand. But we do know that concept of a barrel of oil. And it's 100 million barrels of oil per year saved by our use of plastic. If we want to say we've got to have a future where we are carbon neutral, this is the number of kilograms of CO2 which are saved by plastics. And so to have a champion, to have a policy that says we want to be carbon neutral, we in fact need to consider how we can use more plastics, not how we can use less. We will have an increased dependence on plastics because of how lightweight they are, because of how low energy they are. But that does not discount the fact that these materials produce waste. And so what we have to do is we have to do a better job of handling this material. This is a picture of Extinction Rebellion. I had the benefit of talking to them outside a Greater Manchester Green Summit event. And it was really interesting talking to them because the general public doesn't necessarily know what plastics are. They would think of plastics as what they would have after they emptied the vessels that they procured food in at the grocery store. They're not thinking about these as the world of polymers that we as material scientists know. So they don't think of plastics as being in textiles or being in those face shields or being in electronics or being in their shoes or being in the adhesives that are attaching them to this wall in the London Stock Exchange. The complexity of our material landscape is adding additional challenges around what we need to do with our waste. So we know we need to use plastics, and we know we need to do a better job of minimizing their environmental impact. So let's take a look at why we use plastics in the first place. Well, in the food industry, so if you go into a grocery store, right, the reason that we're using plastics is because they have offered us an opportunity to transform the shelf life of materials. So we do not have so much food spoilage. This dramatically decreases the carbon footprint of our food industry and allows us to use more of the food that we produce. It has also dramatically improved our food safety standards. This means people don't die. We don't have as much salmonella, right? Those are things that we need to keep doing, right? If you look at the different meat packages up at the top here, and you were to say, which one's sexiest? Well, it's this one on the left, right? And this is because it's a better cut, but really it's because it demonstrably looks better when on a black background. And so the marketing people have recognized this. You put that onto a black plastic package, it looks better, you can sell it for more money. Sexy looking meat drives purchases. But this package here is much more difficult to recycle than any of the other packages. And so when we're making a decision about our plastic flows, and it's not actually for a real purpose, of course we should stop doing that, right? And so we need to be careful in terms of our legislation on what we're actually doing. But many people who aren't materials scientists would look at that and say, okay, that's just like a piece of plastic packaging. Let's go and recycle it. Well, the challenge here is how complex it is, because this plastic tray or a plastic reinforced paper tray is going to be one type of material. The plastic lamellar film that's stretched over it is probably 5 different micrometer sized layers of plastic. We've got an adhesive and a heat seal attaching this to our package. We've got a plastic reinforced paper label and an adhesive behind that. And then underneath this meat, you often find this absorbent meat juice soaked plastic material as well. And so when we think about what could happen to those materials to try and recover value so that we can use the plastic that we need, but retain value from it, we could say, well, how many people would be willing to wash this plastic tray and put it into their recycling bin, and then we can go and recycle it, right? And that'll be a certain percentage of people. It's actually pretty high. You know, if you look at trays across the UK, how many people would do it? We're really looking at upwards of 90% willing to do that, whether or not the local councils want it or not. Fewer people are going to be able to do that with the film, right? They're going to feel it's a little bit gunky. It's harder to use, it's harder to process. It's going to get stuck everywhere. And no one is actually going to take a meat soaked juice plastic thing and stick it into the recycling bin. And so this is the second thing. We've got to be able to plan what we do with this material based on societal realities and not our wishful thinking. And so designing your polymer or designing your material with information from how that's actually going to be used, how society is going to interact with it, is essential to making something more sustainable. What about our new world, right? We're now in this coronavirus land where we've gone from having a demonization of plastic to having a real recognition of how essential it is. So plastics are there because they prevent infection. They're very consistent. They're easy to make. They're easy to make in a sterilized way, and they're cheap and they're disposable. And so we need to keep doing these things in order to prevent infection, in order to prevent coronavirus, right? Do we need all of the plastics that are in a hospital? No, we've got projects now that are looking at surgical kits and how much excess there is. Do we need to do this if this is just about convenience? Do I really want the general public in Greater Manchester to start wearing a face mask properly? Yes, all those things. But really, we need to keep recognizing the value of plastics in our medical profession. Why do we have wet wipes though, right? When did we suddenly become unable to wipe our bottoms with toilet paper? There's a real problem we have with plastics, especially when we think about them in the medical field and what they say on the tin and what they do in real life. So the big challenge around wet wipes isn't that you're using them, it's that people flush them down the toilet. And so if you look at this material, it says 100% biodegradable baby wet wipes. Little other things on there, it says it's plastic free, 0% plastic. We've tested both of those things. Actually, it's about 90% plastic if you take away the water, and it's about 30% biodegradable. It's actually an exceptionally good way to make microplastics. But because we have an inaccurate way to actually measure these things, and we don't really have a legislative framework around what is sustainable or not sustainable, we have real challenges around communication on what this means. When we have something that's marketed as being 100% biodegradable, people feel completely comfortable chucking that down the toilet, having that go into our sewer system. And it has created demonstrable difficulties in how we process our waste because they basically make the wall ties in fatbergs. So what is sustainability? Like, what are we actually then going to try and do? How are we going to solve these problems? Well, as a polymer chemist, I'm going to think about that material bit first, right? But we have to recognize that that holds societal value. We need to communicate that. We've got to be able to use that, but use it in the right way. And so by using it in the right way, we need to think about the fate of that material first, right in the beginning, right? And that means we've got to think about reuse. How can we reuse this material? Is this going to be reusable? Is it going to be more robust? We've got to think about recycling, and that might be recycling from a mechanical perspective or a chemical perspective. And we need to be able to degrade these materials if we can't capture them. And only when we can't do that should we be thinking about something like energy from waste, the pyrolysis or the incineration of these materials. And so really what that means is that I need to have a method or a route to be able to understand what that value is through all parts of its life cycle. And so by following it along the life cycle, I can retain that value as best I can. And so instead of saying we want to have a plastics-free world, we want to have a world that values plastic and prevents its release. So this is a place that recovers the value from all plastic we see. And it becomes about a sustainable system rather than a sustainable plastic. And to close this bit, I want to highlight that what we do now is we talk about the ability of a material to be, say, recycled or composted or biodegraded. And what we need to do is we need to move to the past tense terminology. It only matters the fate of that material. So if a material is recycled, if a material is composted, if a material is biodegraded, that's what matters. We have to develop things that match our waste management systems that we have. So obviously I care about people understanding this, and this leads me to do all kinds of stupid public engagement events. These before I came here, so in the bottom left, the kind of very vibrant trousers were before I came to the UK called my public engagement pants. And I very quickly found out that calling them that in the UK would be inappropriate. So I do have a pair of public engagement pants, but I don't have them on show. But the thing I really wanted to say in terms of take-home message number 2 is that you've got to find something that you're passionate about. It might be really specific and it might not be topical in this kind of like BBC style way, but you've got to be able to drive your work by your passion. And being passionate about something is really essential to being able to put the work in and kind of like very much work hard to drive that forward. It's also important to recognize that this is going to evolve. I started as an inorganic chemist and now I'm doing waste management, right? It's been a big journey for me in terms of changing and learning new things. You want to think about why you're doing something. And this is important because if we're not self-reflective, we kind of get trapped in loops. Think about why the research you're doing is important to you individually, to your partners, to whoever you're working with. And that's going to help decide on which bits are important and which you can kind of leave behind. And you want to be able to share your why with others. We're in a world now where it's easy to get news on everything. It's easy to get a hot take on all things that we do. And there's a lot of mistrust that comes from that. And fake news is a real problem, especially for science. And so we have a responsibility to communicate that, to champion truth, to question policies, to disrupt norms. And that means we need to engage more of the public with policy and industry to ensure the changes that are coming are fit for purpose. Part 3, what? So I figured I probably need to appease some of the science nerds in the audience with a little bit more detail on some of the stuff that we do. The first is a bit of a historical montage that I'm going to go through quite quickly. So we started way back in Prince Edward Island days, looking at some vanadium catalysts that were used for controlled radical polymerization. We were the first people to really use vanadium in this way. We did a lot of work on polymer stars that were biodegradable. And really interesting, after all this time, we're now restarting a whole project on polymer stars that are biodegradable in an industrial collaboration, which is pretty cool. We did a lot of work on iron catalyzed controlled radical polymerization. And we're really, really proud that this was iron. But all of our industrial partners at that time only cared about one thing, and that was that we could turn the purple stuff to white. Because when you think about making a bunch of plastic, it's really important that that's white so you can sell it to people. It's great to have a purple lawn chair, but not everybody wants a purple lawn chair. So that I guess square peg for a round hole type thing. It's really important to know what industry wants before you start trying to do that work. And through that work on iron, we've done a lot of work that's collaborative. And I think this is also really important. When you don't know how to do something, you can go and spend a lot of time learning how to do it, or you can go and find the world expert on how to do that and really try and drive that forward. And we've really been able to do that throughout our career. And this was an example where we had to do some moss barrier spectroscopy. And I still don't understand what this slide means, but you know, we were really able to drive that project forward because of that expertise. And what was really neat, and this was at this transition from Prince Edward Island to Edinburgh, this is an example of a collaboration with Steve Thomas. Just over coffee, you're able to say, oh, well, like we have this catalyst and we use it for polymerizations. Can it be used for something else? And you know, Steve's able to take a simple catalyst framework and start doing something completely different with it, and really get quite a cool paper out of it. And so being able to valorize one's own ideas by giving something to someone else, by collaborating in that other direction, is really important. And this is especially true when we tried to get into more applied stuff. And so I think Sarah had mentioned medical diagnostics, which is something that we really had as a major focus of our group before we moved down to Manchester, and would love to pick back up someday. We just don't have the time, where we were able to develop these morpholino cross-linked polymers that were able to sense to quite low values, picomolar values, the presence of very specific microRNA units. We since then have done a lot of work with titanium mediated radical polymerization that was featured on the cover of Macromolecules, and a sequential multi-catalyst step to make what are called PEGOs. So they're sugar mimics that are entirely synthetic that have a ton of different control over stereocenters within the backbone. I'm not going to talk about any of those things. I'm actually going to talk about 3 different stories that each are kind of, I would say, a foundation for the major research areas that we're working in right now. So I'm going to talk from right to left here in terms of 3 things, leaving Frodo as a temptation for the end. And so the first one I kind of wanted to jump into was this idea of having biodegradable polymers. So I talked before about, you know, a lot of these biodegradable polymers aren't fit for purpose. Either they don't have the properties we want, or they don't actually biodegrade. And a lot of this is down to some synthetic challenges that we see around how we make those materials. And so we could make those from an alpha hydroxy acid. We could make those from a diester. We could make those from a O-carboxy anhydride. But really, there's synthetic challenges around each of those. And so we invented a new methodology to be able to do that, which are these dioxylane rings, or we call DOX monomers. And from that, we can make lots of different frameworks, and in particular had an interest in this polymandelic acid. And so the idea of this is we can take an alpha hydroxy acid, we couple that to either acetone or formaldehyde to be able to make our monomers. This is a very clean and efficient step. And then we do this polymerization using a metal-based catalyst to be able to make the polymer. And then we'd be able to degrade that back down to the alpha hydroxy acids, but also capture this formaldehyde and cycle back through. So we want it to be a circular economy, so to speak. The monomers are really easy to make. We can make them at scale. Even in our labs, we can make them hundreds of grams at a time. Very, very efficient process. And we can also make the polymers really easily. And importantly, for those of you who are chemist-based, we see a retention of chirality. And so oftentimes you can change the properties of a material by being able to control what's called the tacticity. And we naturally get either an atactic or isotactic material solely based on what our input starting material is. And so we do a lot of process optimization in the group, trying to understand why a reaction works, why it doesn't work. So this slide in particular is a couple years of work by Yue Chao, who's a postdoc in my team, is now back in China. And this was all to try and increase the molecular weight of this material up to a scale that would be useful. That currently, we transfer some of that material to a couple industrial partners, and are looking at different things they can use it for. I think it's important to remember why you're doing something and whether or not it's green. So, you know, the things that we looked at as chemists were whether or not these racemized, or whether we could retain our chirality, what our glass transition temperature was, so when our polymer started to get a little bendy, whether or not we could recycle this paraformaldehyde. It's actually really easy. It forms as a crust at the top of the reaction vessel. We just scrape it out and chuck it back in. From a safety issue, we care a lot about toxicology, so we needed to make sure that there was no formaldehyde in the product. And really this comes down to cost, right? And so we were able to decrease the cost of this by about 250 times. Still much more expensive than polystyrene, which it mimics in properties, but really offered an opportunity to be more sustainable. We can use that same framework for doing all kinds of different collaborative work. So this is a collaborative work with Alison Hume, who's up at Edinburgh. We were able to attach alkynes as a Raman active tag, which could then show up in cells as a diagnostic. And you can see you can either use a deuterium labeled or an alkyne labeled polymeric system. And we got much better signal to noise ratio for the alkyne system. And in a new collaboration with Adisa Azapagic in chemical engineering, we were actually able to go and start looking at the life cycle analysis of this material. And this is something where people, polymer chemists, often don't really publish this stuff. And it's really important to recognize how important this is. So I've just talked about why this work is really important and really cool and stuff like that. But when we got this first data, we were like, oh, okay, this is great. So this is the best process right now. So the one that says OCA small lab. So 20.5 kilograms of CO2 per kilogram of product. And we were able to reduce that to 14.2 kilograms. It's like a big savings, right? If we were to switch over to that material. Really recognizing that mandelic acid was a big player here. But it's really important that you show all of your data. Because if I compare that PMA that we had prepared to all of the commercial products that you would traditionally use in packaging, you can see how awful we are, right? And so even though this looks sustainable, I've made a biodegradable material, it's entirely from renewable resources, it's actually really quite bad from an LCA perspective. So just because something looks sustainable doesn't mean it is. We would have to dramatically change the route we're using to make that mandelic acid in order to bring this at a competitive level. But that doesn't mean that this doesn't necessarily have applications, because when you think about how this flexibility works, it just says that you need to be targeting, instead of those bulk materials, those specific materials where you're never going to be able to capture and therefore have to prioritize biodegradation. And so we have a number of industry partnerships in this space, looking at adhesives, looking at formulations, and looking at cross-linked materials. And these resins are really a growth area for us to try and take this forward and look at our industrial collaborations. I can't really talk about the specifics of that because we haven't been able to patent it yet, but hopefully soon. So story number one, this looks sustainable, right? And we have to be really careful about whether it is or not. Story number two actually comes from a challenge given to me by my line manager up in Edinburgh, who said I was working too much in industry and I needed to do something more fundamental. So I went back to my roots in boron chemistry in my undergrad and phosphorus chemistry in my PhD. And we came up with this idea that's based on what are called frustrated Lewis pairs. So frustrated Lewis pairs, we take a Lewis base and a Lewis acid, which normally come together and form an LPA or Lewis pair adduct. However, if we decorate these with really big groups, then those two units can't really come together, right? They sort of squeeze against each other and they can no longer form this bond, but they still have that latent reactivity. And so you've trapped it in an uncomfortable state, so it's frustrated. And so if I take that frustrated bit, I can do, from a small molecule perspective, lots of interesting chemistry. And I just show two examples down here in terms of being able to cleave hydrogen or being able to activate weird small molecules. And so what we said, sort of as a hypothesis, is what happens if we put these in polymeric systems? Can we make a polymeric frustrated Lewis pair? So to be able to do that, we invented some monomers, developed these polymers, and then had this particular small molecule that we're using to introduce cross-linking or gelation. This actually works really well. This was a painful experience for Meng Wang to do to get to this first generation material. But when we go and take that solution of the two polymers, they have no interaction. We squeeze in this diethyl azodicarboxylate, and immediately we get gelation. So gelation is very, very quick here. And over time, this is going to change. So initially, we get a kinetically trapped gel that changes into a thermodynamically trapped gel and squeezes out a little bit of liquid. Meng is going to come in and hopefully turn over the vial sometime soon. And I keep asking him to get a shorter video, but well, we're locked out of the lab, so he can't. We'll use that as an excuse this time. So that polymer gel looks pretty neat. I mean, at least the hypothesis worked. But what was pretty cool about it is that it's actually a self-healing material. So the bonds that are between those bonds are dynamic, which means that we can shape that onto a rheometer plate. We can squeeze that material together or add a little bit of solvent and get very, very fast self-healing of that different framework. We can do that from a dried gel as well as a swollen gel. It just takes a little bit longer. We need to add a bit of solvent in to facilitate that. These are also thermally responsive as well, so I can heat that up and then release those bonds and release the small molecule that's bonded into the system quite easily. It's a relatively low temperature, 70 degrees or so, to be able to do that transition. So this was really our first foray into playing around with rheology, and we've been really quite pleased with the access to rheometers that we get here. And this has allowed us to sort of explore this self-healing material, understand how it acts as a supramolecular gel, and sort of start to play around with tuning this ability. But I think we were always trapped by the fact that we're using quite an esoteric small molecule. And so we turned to what we call next generation systems for that. We're now on generation 3. And again, I can't show you what this is, but it's actually a pretty cool, it's much easier to make, and it's much more flexible in terms of its synthesis. But it is a powerful platform that we're now basing a lot of our research around. The first image up here is us sensing a variety of different small molecules, some of which only differ by a single carbon. And so we have very fine control over what we see and what we're observing colorimetrically, and also in the properties of those gels. We have other additives that we can add in that create viscoelastic behavior that we can explore as biodegradable or as reversible adhesives. And we finally, and this is probably the most important area, have a much more broad array of different substrates we can use, and are now looking at exploiting these in catalytic transformations. And so that's a cool platform that we're growing. And the third one, why in the world do I have Frodo up on the screen? Well, you guys will be aware of Lord of the Rings and that moniker, one ring to rule them all. And so I was in a meeting where we were trying to come up with sustainable waste management systems and came up with this phrase, one bin to rule them all. And that's the last story I want to talk to you about. And this was done through a consortium approach. I'm principal investigator of Rethinking Resources and Recycling, which is an EPSRC grant that brings together more than 20 academics and 30 industrial partners, and importantly is very interdisciplinary. So all of our projects are purposefully set up to have an interdisciplinary team associated with it across materials science, social science, and manufacturing. And it brought in a resource from the Henry Royce Institute and the Sustainable Consumption Institute, and really started to try and merge those together to do something a bit different. And so this One Bin to Rule Them All project is in collaboration with Helen Holmes and Maria Sharmina, and supported by postdoc Martin Burgess, who works on the project. And this was entirely derived from stakeholder interactions. So we brought industrial people together. They said, well, what are the challenges? Why can't you recycle more? And it started with this idea of an imagined future, where anything that you think is plastic, you can put it into one bin and we will handle it, right? Same as what we do with water, where everybody just puts whatever they want down the loo. We've got to have still a responsibility on how we curate that waste. All of that waste management is our responsibility. And so how do you then get to that stage? So in that imagined future, what are the roadblocks? What are the contestations? What are the fracture points that are preventing industry and a variety of different stakeholders from getting there? Well, really, this is about eliminating plastic release. And what we talk about is retaining things in the highest value condition. So what's the best way that we can keep that as the most plasticky plastic material that we can get? And we use 3 different cycles to prevent that release. So reuse, mechanical recycling, and chemical recycling to always derive value from it. And so this is the idea. You start with having one bin, and you basically embed a marker or print a marker on, or have a variety of different markers on that system. And you can identify at source when you're sorting it, whether that is best placed in reuse, and reuse has a very broad definition, or whether that's best placed in mechanical recycling, where you could potentially track the number of times this has been recycled, or through chemical recycling. And this should be as selective as possible to basically make virgin feedstock to make new products out of it that retain or recreate that same virgin property. And you can see now from the right-hand side how important industrial collaboration is. So we really work hard at building our industrial relationships, and importantly, create these relationships across the supply chain. And so we're often bringing those partners together. And so they've never even talked to that, even though they're right adjacent to one another in a supply chain. This is the first time that they really understand what the challenges are at different points in that industrial flow. So from a research perspective in materials, we sort of have 3 focus points. We have an interest in making things more robust until they're recycled, but retaining the ability to recycle them at the end. And this is particularly true of multi-materials and composites. We are looking at what we call tipping points in recyclates. So how do we know when something should go from being a mechanical recycling pathway to a chemical recycling pathway? And improving the selectivity of chemical recycling processes, is particularly around polyester synthesis. Just some takeaways in terms of this. So what do we need? Well, the reality is that this is not just a material science problem. Material realities are 1/3 of the challenges that we face. We've got to deal with the social realities. If you don't understand what someone thinks is plastic, you're not going to know what goes into one bin, and you don't know the speciation of your waste flow. And it's also got to deal with the economic realities. This is a new proposed business model. How that transfers value across different players in the supply chain is important. And so this has been great because I've had to learn a lot of terminology and ways of working in social science and economics. And Maria and Helen have really helped with that. And the key takeaways are we need interventions in terms of standardization. This is a policy issue. We need investment in infrastructure. That's a policy issue. We need a creation of value, higher value recyclate. That can be a policy issue. We need collaborative business models that can be enabled by policy change. And we've got to be able to continue to build these interrelationships between companies. And this has led us to have a lot more role to play in trying to influence and shape policy, both at Bays and DEFRA here in the UK. And how do I do all this? Well, I do all this because of what I consider to be a remarkable opportunity. So the Henry Royce Institute is the UK's national face when it comes to advanced materials. And it's really an innovation arm that tries to enable innovation and enable collaboration across the UK. My focus is on sustainability. Eventually, Floor 6 here is going to exist once we get construction teams on site and make that happen. And in here, we've really got three foci. We've got the ability to do synthesis, the ability to look at this hierarchy of materials and decide whether or not something should go through degradation pathways or recycling, and then an ability to actually look and quantify biodegradability or recyclability. And again, this is building on our industrial relationships. And so supported by the European Union, we've had this 10 million pound facility agreed, which is going to be the Sustainable Materials Innovation Hub, which has a virtual opening very, very soon, but facility opening hopefully early 2021, that really allows us to enable both our independent research and the collaborative research that we thrive on. So that's really it in terms of those three science stories. And it really just leaves me to kind of say, you know, you don't have to be limited to the problems that you come up with. So solving the problems of others can be really fun. And I think that's what's driven our relationship with industry. And it's very different perspective, I think, for business engagement. And instead of trying to pitch our inventions, right? We really need to be pitching our expertise. And that means that we need to be able to think laterally, think very disruptively, and think outside our traditional silos. So we don't always have to push our solutions. We can push our expertise as a way of understanding a particular challenge. So last thing, and I promise I'm almost done because I'm desperate for a beer. Part 4 of the Who. This is all about me, and I keep saying me, but the reality is you know, all of us academics are built on the hard work and rare tears of our teams. My current group is up here at the top. The people in red are the people whose work has been showcased particularly, but really all of them are delivering exceptional things. I've been very blessed to have a team that matches me in my spirit and in my hardworking attitude and my ability to really think outside the box. And I think that that's key. Really keen is to I'm really keen to recognize collaborators, both industry and outside. You know, names that are there are complemented by a lot of emerging ones that, you know, we're just starting to do some neat stuff with. And of course, finally, you know, funding, because we're really driven by our ability to do stuff and having the money to do it. And really, I've had a lot of diversity in terms of different organizations that have given us support, and I'm extremely thankful to them. So I thank them in particular, but kind of wanted to do a bit of a montage here. It's really important for me to come back to this idea of mentorship. I think that mentorship is so essential because it frames the future instead of framing today. We've got to be able to train people and train them to be exceptional scientists and future leaders, not okay, right? And so having ambition and imparting that ambition in them and an ambition to really be great is important. Mentorship happens in both ways. And so in the top left-hand corner up here are people who have really been influential to me. They have changed the way I think about the world, about science, about what we do, and have been extremely important. And I'm blessed to have an exceptionally international group. And so the flags are people who have been part of my team, and you can see we're coming from all over the world. And I think that's been important to ensuring that we have objective views of everything that we do. And I'm so thankful to the team, many of whom are on the call today. including past people who are on the call today. And I'm really blessed to have that experience. The final thanks, of course, goes to the family, right? And that's not a traditional family unit, but we've got a wife and 2 dogs who are exceptionally supportive. Callie, who's the black one on the left, she's actually a registered therapy dog. And I must say, being trapped home in lockdown with a therapy dog is not that bad. So hopefully we're all back in lab soon. But yeah, thank you all for your time and attention.
Thank you so much, Mike. That was a very engaging and really informative presentation. It's an absolute pleasure to have you here at Manchester. I wonder if we could try and do, I haven't tried doing this before, if we all just unmute, just would like a round of applause, if we all unmute. Thank you.
Congratulations, Mike.
We're going to have to ask people to mute again. So we have some questions that we can ask. So what we're going to do is we're going to use the little blue hand raising symbol, which you can find if you're from a laptop, if you just move your mouse, if you're, I'm sure everybody's very familiar with Zoom right now, but if those who are not, if you just move your mouse, you should see a participants just at the bottom of the toolbar. If you click that, you should be able to see a blue hand that you can raise. If you're using a mobile screen, then you should be able to raise your hand on the bottom left-hand corner of the screen. I'll be able to see those in order. So please do start raising your hands if you want to ask a question rather than use the chat function, okay? I'll take chair's prerogative and kick off the questions if that's all right. So Mike, you asked, you talked a lot about legislation, and it sounds like that regulatory influence is very important to you. You said it wasn't just looking at the material science or the polymer chemistry. There's lots of things we need to put into place to make sure that we really can make a difference with this technology. How do you propose, or how are you engaging with the regulatory procedures or that legislation process, and what can we be doing as an academic society in order to improve that?
Yeah, I mean, I think first of all, it's recognizing that we have a university that has all kinds of different parts, right? So policy at Manchester is actually a really cool function that we have that is both able to signpost and guide and try and shape that. We, in any of our big consortium projects, invite people from DEFRA and BAYS to join those projects to ensure they get information. And then when it's something that's bigger, we'll write a white paper. So we're writing a white paper right now from the RE3 team and the other PRIF projects on what we think the takeaways are from that last year of research. And then it's finally responding to consultation. So it's often an ask, right? So there'll be some message that goes out saying, you know, what are your thoughts on this? It takes time. This is really it. It's a commitment to put that time in to be able to try and deliver on it. But those are the mechanisms that we choose.
And you talked both at the start and at the end of your presentation about mentoring being really important to you. What top tips would you give to those early career researchers in sustainable materials field?
I think that they're it's not necessarily sustainable materials that advice would go to, but I would say it's being mobile, right? I think oftentimes I look back on the first grant application I wrote and how crap it was. And I had a particular idea that I thought was really, really good and was going to be very important. And I think not being precious about one's ideas and being quite mobile and being willing to shift fields and to do things differently is really important. So yeah, be ambitious, but be flexible in terms of what you want to do your research on.
Perfect, thank you. And again, please, I do encourage you to raise that blue hand if you do have a question. I'll just have one more question, if I may. You showed in the RE3 grant that very large grant that you're involved with right now, there's lots of industry collaborators in there. And I know when you showed kind of the meat packages, and you were saying that, you know, dyeing the polymer in that circumstance black isn't, even though it's good for industry because it can charge more, right? That's not going to be an attractive option for sustainability. Do you have lots of different kind of political negotiations you need to take into account when you're speaking to all your industry partners in that RE3 proposal, and how do you handle that?
Quite a few of them are on this call right now, so I need to be careful, right? I'm looking at Ian Ferguson is just to my left from call. So I mean, I'll be pretty explicit here. There's a reason that Co-op is our preferred grocery store partner moving forward, because their ambitions match our own. I think that both Ian and Rob have really been very open to sharing why they can make their certain decisions and why they can't, and really open to change and to push things forward. So I would say that it's been a bubbling to the top somewhat of those partners, and then really very significant persistence when it comes to key people. So it's very difficult. It's been very difficult to secure the support of Suez and BIFA on that sort of waste management side of things, because they're really in the thick of it in terms of how that would change their business. And so I would say it's really bringing a community together and being persistent in getting the right people in the room, and to encourage it not just to be our voices, right? So oftentimes if we say something, then maybe we'll be dismissed. But if you get the two people on the opposite sides of someone's supply chain saying the exact same thing in terms of what's an enabler, that can be pretty powerful. So letting the industrialists speak is very helpful too.
That's excellent advice, thank you. We have a question from Maria Shalmina. Can you ask please, Maria?
Hi Mike, thanks very much for your lecture. I really enjoyed it. Really good to get to know you a bit closer, you know, because we've just started working together. So thank you. I have a question about one of the take-home messages that you've given us, which was questioning the norms. And I think that often involves speaking truth to power, you know, challenging the mainstream journals potentially, and established academics like you and me. And it's probably easier for academics at a more senior stage in their careers, but riskier for early career researchers in terms of their not so established careers and dependence on those, you know, more powerful academics. What would be your advice for early career researchers in questioning the norm?
I agree. It's unfortunately risky. I've always done it. I think even back when I was an undergrad, I probably was disruptive more than I should be, and I've been lucky to have not gotten too much trouble for it. No, it's a balance. I would say you need to go and talk to other people who you trust. And this is really where mentorship can be very important, is if you have the right mentor, that mentor is going to be able to build a community around you to support that. And so whenever you feel that something needs to be said, it's really important to kind of do a little bit of groundwork to ensure that you're supported before then. But I would always recommend not putting up with it. I just don't agree with standing back and saying nothing when something is clearly wrong. So find a community that will support you and then speak the truth to power, as you suggest.
Thank you, Maria. And Brian Saunders has a question.
Hi, Mike. Really enjoyed your talk. It was fantastic. Congratulations. If I may, can I ask a technical question? Because you did put some chemical structures up. Yeah. And it's about the frustrated Lewis pairs. With the frustrated Lewis pairs, there was a small dinitrogen molecule which brought them together and gave the gelation and dynamic. Would it be possible to use part of a copolymer to have that moiety within the copolymer and then have it always present?
Yeah, so if you do that, right, so if you introduce that group to start, then it's not triggerable. So when you first put those together, you form the gel. And so that would almost be a Lewis pair adduct instead of it being frustrated. So we wanted to get something which was triggerable and then to be able to go backwards with it, which is why we kept those separate. You're completely right. And that's a whole field in and of itself, to be able to take a Lewis pair interaction and have that as a triggerable dynamic gelation process, which works well.